Okay, I'll get started. So last lecture we actually introduced some very basic concepts about reinforcement learning, like actions, observations, and rewards, history, which is based on the sequence of these things, and we defined some problems like prediction, which is trying to figure out how valuable each state is based on a policy. Where a value function is defined as the long-term discounted rewards you will get starting from this state following that policy, and the problem of control, which is basically what is the optimal policy, what's the highest value function we can see. And in fact, we saw simple examples like this where we have a grid world, there's a finite number of states, and we ask questions like what is the value function for a uniformly random policy for a randomly moving agent. And in this grid world, every move gives you -1, with two exceptions. If you actually come to A, you jump to A prime and get +10, and B makes you jump to B prime, gives you +5. So if you have an agent that basically lives in this universe for an infinite amount of time, then what can we say about the various values of being in various states? Now, and so you showed some surprise that this question can be answered because it's not a finite game. How do we know? The thing is going to play forever. And in fact, if we don't use a discount function, then the answer to this question is either +infinity, -infinity, or 0, right? So whatever it can do, if there's a, if the random actions basically have a overall positive expected score per time period, then if you play for an infinite time period, you're going to get +infinity. And that basically is related to how often you actually get to A and get those 10 points, etc. However, as we see in this answer, we don't have infinite values, we have finite values. So where did this come from? This came from discounting. So if we actually compute our returns by discounting future rewards as compared to current rewards, we can actually solve these types of problems. Or we can give finite answers as to the value of the different states. So today we're going to learn how to do that. Okay, so that's our goal. We're still working on toy problems, meaning we still have a finite number of states, small problems. We can actually solve these things using small amounts of computational work. There's still no neural networks in sight, but I think it's important to learn how to solve these small cases to build intuition into the reinforcement learning problem. Okay, so this type of game, when we represent it mathematically, is called a Markov decision process. And a Markov decision process basically involves obviously decisions because the agent is deciding to act one way or another. It involves rewards. It involves these probabilistic transitions between states. And before facing the whole Markov decision process as a whole, I want us to go there step by step. So first, let's talk about just Markov process, what that means. And then, so basically, a Markov process is something where there is no actions and no rewards. Okay, so we have a fully observable environment. We have states. We have probabilities of transition between states. So if you're in a particular state at time t, there is a probability that you will end up in state st+1 for various values of st+1. And the reason it's called Markov is basically this probability only depends on st, and it doesn't depend on anything that came before st, given st. Okay? So if you were basically agent who couldn't move and who couldn't actually get any rewards. This would be the universe you're living in. In such a universe, what questions would be meaningful to ask? A value function doesn't make sense because you don't have rewards. A policy doesn't make sense because you don't have actions. So what kind of interesting mathematical questions can we ask for this passive observer that has no rewards? Right, so we can ask things like, what is the probability that you will end up in this state or that state, right? And does anybody know how to answer such questions, how to solve such problems? Basically, as input, I give you this matrix. Right, so this is basically the state transition matrix. There's a finite number of states n. And the ijth entry of this matrix basically gives you the probability of going from state I to state j. So that's all you need to know about this type of system. So what can we do with this type of matrix? Any ideas? So here's a matrix P. These are from, these are to. So if I am in a particular state, then the next state is given by a particular row of this matrix, right? So the probabilities of the next states are given by a particular row of this matrix. And how do I get a particular row of this matrix if I wanted to actually do it with a vector? Multiplication or something. So I can basically have a row vector that's a one-hot vector. Here's a 1 and everything else is 0. And if I multiplied this particular row vector with this P matrix, I would get a copy of this row, if this is the ith component, and this is the ith row. Correct? That is correctly? So this is your state at time t. We know exactly where we are at time t. And this would be the probability distribution for all the states at time t plus 1. Okay? Okay, so there are. So then, what do I do to figure out where I'm going to end up at step time t plus 2? Well, I can take this vector and multiply it with p again, right? So st plus 1 is not a one-hot vector, it's a probability distribution. It's basically saying there's a 50% chance you're here, there's a 20% chance you're there, etc. But taking that and actually multiplying with p again is going to give you st plus 2. If I multiply this again, st plus 2. And remember my matrix multiplication notation, right? So I kept doing this for, this is A, this is B, this is A times B. The way I write these things. Okay, so then we see that this has to do with some linear algebra, and we can ask some linear algebra questions. For example, what kind of vector would not change when multiplied with p? So an eigenvector with an eigenvalue of 1 would not change when multiplied with p. What does that mean? What does that vector, that eigenvector, represent for our problem?
Steady states.
Right, so that distribution, whatever that distribution is, represented by that eigenvector. When I multiply with P, doesn't change. It's the same distribution. So that means in the steady state, you would basically have those probabilities. Because once you have those probabilities, they don't change anymore when multiplied by P. Any questions about these so far? Okay. So formally, we basically say a Markov process or Markov chain consists of S and P. S is a set of states, and P is that matrix that show the transitions, and that's pretty much the interesting questions we can ask about a Markov chain. So here's an example that we're going to keep enriching throughout this lecture of student's day. So I have states. So you have 3 classes. You like going to the pub, you like sleeping, and there's also doing Facebook on your phone. And this particular student now is basically only a passive observer of his or her life. They're not making any decisions. They just float wherever fate takes them. So if you're in the first class, after that, there's a 50% chance that you're going to go to class 2 and 50% chance that you're going to go read Facebook. And you're not taking any decisions or deciding any policies. You're basically being drifted passively in the universe. And also, you have no utility function, so you have no rewards. You don't care whether you're doing Facebook or class number 1, etc. So this is the student Markov chain. So what we can do with the student Markov chain is, as I said, we can actually compute some steady state probabilities. We can generate episodes, right? So we can basically assume that this student starts at class 1 always, and then do some random coin flips and see what different episodes there are. In this case, there is some absorbing states like sleep. There is no way out of sleep, so every episode ends with sleep. And we can construct a probability matrix. So let's see. If I'm in class 3, there are 2 ways out of class 3. If you finish class 3, there's a 0.6 chance that you will pass, and 0.4 chance that you won't pass, in which case you go to the pub and then go back to class 2. So, and that's represented by this row here. Here's class 3, 0.6 chance of passing, and 0.4 chance of going to the pub. So this is the P matrix that we saw earlier. So we can take this matrix, look at its eigenvectors, and that will tell us things about this system. Now, let's add rewards to this infrastructure, okay? So we still have S and P as before, and now we're adding rewards R and a discount factor gamma. Discount factor is also important because of the reasons that we saw earlier. So S is still a finite set of states, P is still a matrix, R is a reward function associated with every state. So what does that mean? It doesn't have to be a deterministic reward, right? So there can be a probability distribution maybe. So this function basically gives us, if you're in state S right now, what is the expected value of the next reward you're going to get. The reward might be different from time to time, but this function actually gives you the expected value, which is all you need to calculate certain things. And we have gamma as the discount factor. And here's what our student, this is called the Markov reward process, and here's the student's Markov process enhanced with the rewards. So we basically added these red R reward values for each state. Okay, now what kind of interesting questions can we ask in this particular case?
Expected reward.
Right, so we can obviously ask, what is the expected reward? And your expected reward is going to be different based on where you are in this universe. So We can ask about expected rewards in certain states. And when we say expected reward, we mean expected total future reward, looking forward toward the end of time. If you're in class 1, if your life starts in class 1, what do you expect from then on till the end of the episode? With gamma being the discount factor of how you add these things up. So let's define these things a bit more carefully. So let's call this discounted future reward thing return. So GT for us means the return. R's are the individual rewards at each time step. So GT is basically all the future rewards added up. So if gamma was 1, it would literally be all the future rewards added up. If gamma is less than 1, then it's discounted. So RT plus 1 is, we have the whole thing, but RT plus 2 would basically multiply with 0.9 or something and keep reducing it like that. Okay? So, any questions about rewards and returns? Okay. So then, yeah.
So GT over there is a sample of a distribution.
Correct. So everything is probabilistic, so we can't actually calculate a specific value for GT at time t because we don't know exactly what states we're going to go in the future, right? At the end of an episode, we can say, oh, this was your all rewards, and in the beginning of time, this was your GT. But before the fact, we can only talk probabilistically about GT. So we can say, if you're in state 1, what is your expected GT? Expected return. And that's actually the definition of value function. Okay, so last lecture, we actually talked about this value function V. It's a function of S, a state, and it basically answers the question, what is the expected value of GT? Return. If you're in that state at time t, what do you expect for the future? So that's the interesting question we can ask about MRPs. Can we ask about the optimal policy? No, because we're not making any decisions or taking any actions. But we can define a value function, and that immediately allows us to ask questions like this. Instead of saying there's a policy, let's say this guy is actually being pushed around by the wind in all 4 directions completely randomly, and that turns it into an MRP because we're not doing any decisions. So then I can ask things like, oh, what is the value of being in this state, or what is the value of being in that state? Defined like this. Any questions? Okay. So here's some examples from the student MRP. So you remember that we were able to generate some episodes before by flipping some coins. We can still do that, but now we can also say what is the value function for this particular episode. What's V for this, or what's G for this particular episode, using a discount factor of 1/2, for example. Okay. So in this first one, we have C1, C2, C3 pass sleep. If you look back, so C1, C2, C3 pass sleep. That's the path we're looking at, and then we're going to collect the rewards -2, -2, -2, +10, and 0, right? So if we had no discount factor, or discount factor of 1, I mean, then my total future reward would be -6 + 10 + 4, right? But with discount factor, it's going to be less. The first -2 is here, the second -2 gets discounted by 1/2, the third -2 gets discounted by 1/4, and the 10 gets discounted by 1/8, so I actually get a negative score, negative value for this first episode. Okay? So if you imagine basically doing this forever, starting at C1 and generating all these episodes, and looking at this value at the end, and taking a big average, that would be your expected value from C1. And that's the definition of our value function. Okay, and if you, so then, okay, the next question is, I know how to calculate this value function for, given an episode, but, if this guy is traveling around in this state space forever, how do I assign a particular value to a particular state? So how do I do this? This is the actual value. These are the correct values for each state. Remember, these are not, so there's a distinction between rewards and values, right? So values are basically all the total future rewards. Actually, this, I'm going to come to this slide later because it's confusing. There we go, this is better. Okay, this is more simple. So let's take gamma equals 1 for simplicity. What does gamma equals 1 mean? Gamma equals 1 means no discount, so I'm literally talking about my total future rewards. Okay? So, for example, take this state. If I'm in this state, there's only one way out of this state. Okay? And that one way out of this state puts me to sleep. And that particular episode has value reward 10, total reward 10. That's why this guy has 10. Okay? But why does this have 1.5? Can anybody tell me? So there is some chance I'm going to go right, some chance I'm going to go up. If I go up, I'm done. So going up means 0.2 of the time I'm going up and I sleep, and my total reward in that case is -2. So that's one term in my expectation. But then there's other terms in my expectation. If I go right, well, it's complicated because now I have two options of this and that. If I go back here, then there's a cycle here, and I can come back and get that -2 again. I can keep doing this forever. So how do I actually solve this? Any ideas? Well, some smart guy named Bellman actually said, the way to solve this is by creating an equation bearing my name. So we have a Bellman equation, and Bellman said the solution should have this particular property. We know from the definition that the value of a state is the expected future rewards, expected GT, right? And if I basically write it out, I know that it can be written as a sum of all the RT plus i's, possibly discounted by gamma. And if I just, parenthesize all of them other than the first one, then this looks familiar, right? So this is again a reward followed by gamma times a reward followed by gamma squared times a reward. This looks like a G, a return, right? In fact, it's GT plus 1, okay? And so basically, I can also, if I take the expectation of GT plus 1, what's the expectation of GT plus 1? It's the value function of whatever state I end up in, right? So I don't know what state I'm going to end up in, but GT plus 1 is basically the expected value function of that state. So, long story short, he says, let's create a recursive definition for V by observing the fact that the current V is equal to the immediate reward I'm getting from this state plus the discounted version of the next V, next state's V. Okay? But you're going to say, well, I don't know what the next state is going to be. And then he's going to say, well, you know the probabilities of each state transition, so basically add them up. Okay, so with this much probability you're going to state 1, take the v from that. With that much probability you're going to state 2, take the v from that and multiply with the probabilities. And that is your expected reward of the successor state. So here might be a little better graphical explanation of this. So this is the current state we're in right now. And these are the 2 future states we might go to based on probabilities. So the current state is called S. The next state is called S prime. And we don't know exactly which one is going to be S prime, but we just call it S prime. And there's a reward involved, okay, for both S and S prime. So to translate the Bellman equation into a form that doesn't use expectations, we can say the value function for S, my current state, is equal to whatever reward I'm getting from S right now, because I know that for sure, plus gamma times this summation. So discounted version of this summation. What's this summation? The probability that from S I will go to S prime. And if I do that, then I'm going to receive the value function from S prime. So this is the expectation for the next step. So any questions about this final line? So this is the Bellman equation, which is going to help us solve this problem. Okay, it's all very clear. Okay, so then go back. So this is the picture with gamma equals 0. What does gamma equals 0 mean? I don't care about any of the future rewards. I only care about my immediate reward, right? So I'm multiplying everything after t plus 1 with 0. Well, what does that mean? That means it's very easy to solve, because basically the value for each state is just the reward you're going to get from that state. Okay? So, but the main reason I put up this particular slide is so that it doesn't actually have the answers and you don't cheat, because now I'm going to ask you to solve this student MRP and find the actual values for gamma equals 1. Okay? So if you understand the Bellman equation, you should be able to do that. So Bellman equation is something like a consistency check. If you can find numbers for each of these circles, so that each circle's number is equal to the reward of that circle plus gamma times the the expected value from the other circles, then you're done. So you have 5 minutes to solve this. And feel free to ask questions.
So the gamma was supposed to be 1, right?
Right. So to keep things simple, the discount factor is 1. I can tell you 2 of the answers. So this is supposed to be 10 and that's supposed to be 0. Those won't change. So you only have to answer n minus 2 states. Anybody have an answer? So I guess you can see that it's not a very trivial problem to solve. I mean, if you saw the solution, you can verify it's correct by checking the Bellman equation for every entry. But to come up with the numbers that will satisfy the Bellman equation everywhere is not trivial. So let's at least verify that this is a solution. So at least for some of the values, so this says minus 13. Why does this say minus 13? Well, I have a definite minus 2 reward from this one, and there's a 0.5 chance that I'm going to get plus 1.5, and a 0.5 chance that I'm going to get minus 23. Okay? So that means 24.5 divided by 2 is 12. No, I'm should add that. 21.5, sorry. Divided by 2 is 10.5 or something. Minus 10.5, and then minus 2 is, okay, so it's not exactly minus 13, right? So these are sort of, I guess, rounded numbers. They don't match exactly. But, yeah, so you can basically check all the other bubbles and see that every bubble is basically roughly equal to the immediate reward plus all the probabilities times the neighbor bubbles of the outgoing edges. Okay? Any questions about the Bellman equation? Except how to solve it. That's what I'm going to talk about next. So by the way, as I change gamma, things change. So here's the same thing for gamma equals 0.9. Here's for gamma equals 1. So these two guys don't change. This is always 10, this is always 0 because there is nothing in their future. But the other ones change. Okay, so how do we solve this thing? If you look at the Bellman equation long enough, this equation down here, and write the Bellman equation for every state, one underneath the other, then we can have a vector equation. So in this vector equation, we have a vector of these v's for every state. That's an n-dimensional vector. And there is rewards for every state. That's also an n-dimensional vector. Plus, there is this summation, which corresponds to a vector matrix multiplication. Okay? So if I write this whole thing as a vector equation, it looks like this. It looks a lot nicer. Okay? So V is a column vector, R is a column vector, and then we know P, our little transition matrix. Okay. So looking at this, can you suggest a way to solve this equation where V is unknown? Do you remember your, I don't know, how you used to solve linear regression and stuff using linear algebra?
Do you mean solving this set of linear equations?
No, I mean, okay, so can you imagine some vector matrix manipulations, linear algebra manipulations to express V in terms of the other ones? So leave V on one side.
P inverse.
Exactly, yeah, that kind of thing, yeah. So what I want to do is I want to collect all the V's in one place. So that means if I actually move the right side turn to the left, I will have the identity matrix plus gamma P in parentheses times V. And then if I want to leave V free, I need to take the inverse of that, move it to the other side, and that's basically it. So this equation can be solved directly using MATLAB or whatever, right? So it's just a matrix inverse times the rewards. Any questions? This is one way to solve the Bellman equation for the values. It is impractical for large n because inverting a matrix is n cube sort of operation. And there's a bunch of other iterative methods to solve this problem that we're going to see later. Each of which basically starts with a guess for v, set all the v's to 0, for example, and then update, for a certain number of iterations, update each v looking at its neighbors. And if you keep doing that, eventually it actually converges to the real solution. Okay. Any questions about Markov reward processes or the Bellman equation? So we're going to put the final component in our Markov family of models and make this a Markov decision process. The only thing that we need to add for that is actions. Okay? So we basically we already had S, P, R, and gamma states, transition probabilities, rewards, and discount factor. We're just adding a finite set of actions to this tuple. And we make a couple of changes so that the transition matrices depend on the action, and the rewards also depend on the action, potentially. Okay? So once we introduce actions to this, we now have the full MDP that we're going to use for a while as our model of reinforcement learning problems. So here's a particular Markov decision process extension of our student problem. So these are now actions that the student can choose to take. So if the student is in this state, they can choose to study or go Facebook. And if they choose to study, they go from class 1 to class 2 because they passed their class. But then if they sleep, then they never get to class 3, etc. So once you introduce actions, then talking about policies makes sense. A policy is basically the recipe for an agent about how to act at any given state. And in general, we can define it as the probability of taking action A in state S. So all these probabilities make up a table, and we call that table a policy. Okay? And we represent this with the letter pi. Now, interesting observation that will help us solve some of the problems is that once you specify the agent's policy, then I can basically sort of combine it with the other uncertainties in the environment and turn this into an MRP problem, Markov reward process problem, taking actions out of the picture. So what does that mean? Well, if I have an MDP with those 5 components, and I do know what policy the agent is following, then I can basically come up with 2 modified matrices, P and R, as a function of pi, the policy, that basically gives me, what is my expected transitions given this policy, and what is my expected rewards given this policy. And as soon as I do that, then I basically took the actions out of the whole problem again, and I'm back to MRP, and I know how to solve MRPs and assign value functions, etc. Okay? Any questions about this? So an MDP plus a policy can be turned into an MRP.
Theorem or intuitive result like this one?
It's a very intuitive result, but we can probably prove it too if you'd like. So all it's saying is basically, so let's take state transition probabilities. So in MRP, there is only state transition probability. The agent has no control over those transitions, right? In MDP, the agent has control over choosing certain actions, and those actions affect the transition probability, right? But if we know the agent's policy, then we know that the agent is going to try to move left with 0.6 probability, try to move right with 0.4 probability. And in either case, we know how the environment will react. with its own probabilities of state transitions, and we can combine these two things into just one set of probabilities. If I'm an agent acting with, policy pi, then what is my next state? That's a problem that we can solve combining all of these things together. And as soon as you give an answer to that problem, then you have an MRP. You remove the actions from the equation. Last time I may have mentioned that we have another value function that will come in handy sometimes. So in addition to v, which is the expected return from a certain state, we also have q, which is again the expected return, but this time it's basically from a certain state and after a certain action. Okay? And defining both of these things is sometimes confusing, but sometimes they actually make certain equations easier to write. So, and in both cases now, as opposed to the MRP case, these functions are parameterized by pi, the policy. If you change the policy, your value function changes. Both the v function and the q function changes. They both depend on pi now. Okay? So here's v for our student MDP for this particular policy. So the policy is basically probability of taking either action from any state is 0.5, and there is no discounting. So as soon as I say that, for example, if I'm here, I'm going to go right with 50% probability and go up with 50% probability. And of course, in this case, there is no environment uncertainty. So if I try to take the action study, I definitely end up here. If I try to take the action Facebook, I definitely end up here. So it's sort of a, not very different from an MRP, I guess. The only difference is here, from this state, if I actually take the action of going to the pub, I don't know where I'm going to end up next. Okay? There's environment uncertainty there. So if I actually take the action of studying, then I know I'm going to end up in this state, sleeping. But if I actually go to pub, there might be a chance that I end up in this state, or this state, or this state. So when we're calculating the value functions, we need to take both the action uncertainty and the environment's response uncertainty into account. So everything is probabilistic in the most general case. In specific problems, certain things might be deterministic, like rewards or transitions, but in general, we define everything probabilistically. Any questions? So how would you solve, if I didn't give you these red numbers, how would you solve this problem? Find the value function for this particular policy. Let's say this is the final, which I posted today. I think it's the 5th or the 4th, one or the other. So how would we solve this? Use the Bellman equation, but you tried, 10 minutes ago, and you didn't get anywhere. So how would you do it in the final? Yes, you have to use the Bellman equation, but well, first you would have to basically take the actions out of the picture and convert everything into an MRP, right? So basically you would have to really say, if I'm in this state, I'm following this policy, then what is the probability of me ending up in any of these other states, given both the policy uncertainty and the environment uncertainty. And once you have those probabilities, that's your transition probability matrix, modified transition probability matrix, and you can use the linear algebra trick or, from earlier, to invert that matrix in your head and figure it out, right? Okay. I'm joking. I won't ask any questions which require you inverting matrices in your head. Okay. Bellman equation applies to this as well. So we already saw the first one is the same as before, and Q also can be written recursively in terms of itself. So Q of SA is the expectation of your immediate reward plus, whatever the next state and action you encounter will be, the Q function of those. Okay. Now, I'm no longer calling this the Bellman equation, but I'm calling it the Bellman expectation equation now, because Bellman actually has another equation up his sleeve, which is going to help us solve the other problem we're interested in, the control problem, which is what is the optimal policy. Okay, so there is another Bellman equation for the optimal policy. We'll come to that. But before that, let's make sure we understand the V, the Q, the relationship between them, and the Bellman equations that lead up to that. So in this picture, you're seeing S, my current state. V pi of S is the value function for this state under the policy pi. And then from this state, I can take a certain set of actions. Let's call them A. And if I'm in state S and take action A, then my future value is going to be Q of SA. So this whole thing means that V and Q have to be self-consistent with each other. That didn't make sense. They have to be consistent with each other. Okay? So, and this consistency is given by this equation. So V of S has to be a sum over all the possible actions, the probability of taking that action, and then the Q value of that state action pair. Any questions? This is sort of consistency. How about Q? Well, Q also can be written in terms of V, like this. So if I was at a particular state and took a particular action, I'm here right now, and my future value happens to be, I think, Q of SA. But what's going to happen now is that the environment is going to react to me, and the environment is going to send two random things to me. One, it's going to send me a random reward R, and two, it's going to send me to a random state S prime. Okay? Just because I'm taking a certain action doesn't guarantee that I'm going to end up in a certain state. The environment still can mess with me. Maybe there's wind, right? So, so that means I don't know either what R is going to be or what S prime is going to be. So how can I write Q of SA as a mutually recursive equation? I'm going to say, oh, I don't know what this R is going to be, but I know this, its expectation, its expected value is given by this capital R matrix that was offered in my model, plus the discounted version of my future rewards, which is the probability that I'm going to end up in S prime times the state value function for S prime. Okay? So long story short, here's the mutually recursive definition of V in terms of Q, and here's Q in terms of V. Okay? And in general, I basically have a two-step thing going on. I'm in a certain state, I take an action, the environment responds by giving me a reward and then sending me to a random state. Okay, it's like a game with two players. And I can combine the previous two equations to write a recursive one for V or a recursive one for Q. Okay?
The question,
Yeah.
R of S and A in the last equation.
This one?
Yeah, when we write Q as function of V,
This one?
it's expected as well here.
Yes. R of SA was defined as the expected value long ago. So I'm not going to go there, but yeah, R of SA is basically the expected value of the reward you're going to get in state S if you take action A. Okay? So, solving the Bellman equations is another matter, might be quite complicated, but writing down the Bellman equations should be relatively easy. It's just consistency check. If you know the definition of V and the definition of Q, if you know how these different players probabilistically act, so the player at state S probabilistically chooses an action out of pi, and the environment probabilistically gives him a reward out of R, and probabilistically sends them to another state out of P. So if you understand all of these variables, then you should be able to write these equations. Any questions? So just one example before we move on. So how do I know this guy is 7.4, for example? If I know all the other numbers are correct, and this is the last one that I need to solve, how do I know this is 7.4? Well, according to my policy, there is a 0.5% chance that I'm going to study the action, and 0.5% I'm going to go to the pub, right? So that's the first part. And so that's what explains this 0.5 up here. And if I study, then I definitely get 10. Because I have a R equals 10 here, and then I forever sleep with zero reward, so I get the 10 here, 0.5 times 10. If I go to the pub, however, there's the environment can send me to 3 different places. So I do get the reward 1, but then after that, there's a 0.2 chance that I'm going to go to this particular state and get minus 1.3, which is this term here. And there's a 0.4 chance that I'm going to end up here and get 2.7, which is this. And there's a third chance, 0.4, that I'm going to end up in the same place. So that's this. And if you check this equation, 7.4 equals 7.4 is consistent. So the Bellman expectation equation in this, with these numbers is satisfied. Okay? So even though I may not be able to ask you to invert a matrix, I may be able to give you something like this and say, is the Bellman expectation equation satisfied with these values? Any questions? Again, just like we did last time, there's a matrix form of these equations. Once you incorporate pi into the picture, you can get R pi and P pi and turn this whole thing into an MRP and solve it just like we solved the MRP by inverting this matrix. Okay. So last topic of today is it's great if I have a random policy to evaluate what this policy is going to give me, but my main goal in reinforcement learning is to actually find the best policy. So how do I do that? So we define the optimal state value function V star as the maximum overall possible policies of the V's for each state. And I can also define a Q star, the optimal action value function, as again the maximum overall policies of Q. So this is the best possible performance in the MDP, and our goal is to figure out what are these optimal functions. So one quick note is it says here that the MDP is solved when you know the optimal value function. Well, how do I know how to act? Well, if you do know the optimal value function, that means there is a value associated with each state or each state action pair. So let's say we have the Q function solved already for us. Somebody hands you the Q star. Well, it's very easy to act. If you're in state S, you look at each of your actions and they each have a Q value. You just pick the action with the largest Q value. Okay? So that means solving these value functions is sufficient to solve the best policy. So here is the V star for the student example. And here is the Q star for the student example. So you can look at this in more detail in your spare time. Okay. So this is some mathematical detail, but there is an optimal policy that there might be more than one optimal policy given an MDP, but all of the optimal policies give you the same values. So there is only a single value function, a single optimal value function, state value function, and single optimal action value function. And this is basically what I said before. If you don't know the ideal policy, but somebody gives you Q star, the ideal policy is basically to act in order to maximize Q star. Okay, so optimal policy. All right, so this is where I wanted to come. So Bellman has another equation for us. The last one was called Bellman expectation equation, and it answered the question, if I have an MRP or if I have an MDP with a given policy, what are the values? And Bellman said, well, I don't know what the values are, but they should satisfy these equations where, you know, if I'm in a particular state, my value should be equal to the current reward plus the discounted future rewards or whatever, right? So that was the Bellman expectation. Now, the same Bellman said, for the optimal policy, there is another set of equations that these values must satisfy. So if you can find some values that satisfy these equations, then you know you have the optimal values, which basically tells you what the optimal policy is. Isn't that great? And these are sort of very similar to the expectation equations, but instead of summations with probabilities, we have maximizations. Okay? So what was the expectation equation for V pi in terms of Q from before? Does anybody remember?
R plus transitions times Q.
That's right. So the expectation equation for V was the immediate reward R plus a summation over all possible actions, the probability I'm going to take that action, and the Q value for that action, right? So instead, here we have this. This says, I don't care about all the actions and taking a summation and whatever from them. What I care about is the best action, which should be the maximum, the one with the maximum Q. So if I'm actually acting optimally, then the value for this state should be equal to the value I get from taking my best action, which is the max over the Q stars. So that basically gives me one consistency equation between the V's and the Q's. I can do it the other way. So what is the consistency equation for Q star? Well, Q star, whenever you're in state S and take action A, first of all, you get this immediate reward. There is no question about that, right? But then there is a random event. The environment basically sends you to different states, even though you basically picked an action. That doesn't guarantee you to end up in a particular state, so we still have to have a summation, a discounted summation of this. And in this summation, we're basically saying, this is the probability I'm going to end up in state S prime, and this is the optimal V value for state S prime. So this is the expected value I'm going to get from my next state. So again, yeah, so we couldn't use maximization here. Why? Because we have no control over this transition. This transition is by the environment. So I can't actually pick which S prime I'm going to go to. If I could, then I would put a max here as well. But I can't, so I have to keep this an expectation. So now we can combine these two things together and express V recursively in terms of itself, or express Q recursively in terms of itself. The bad news is, and here's an example. Let's look at this example before the bad news. So let's say that the red 6 was the only unknown value in this graph, right? So here I'm basically saying the rest of these numbers are filled by the optimal guy, and this number has been deleted. So what is this number? Well, I can choose to study or I can choose to Facebook, right? If I study, I'm going to get an immediate reward of -2. What's my gamma here? I guess gamma is 1. And then I'm going to receive an 8. So that's 6, right? If I choose Facebook, I'm going to get an immediate reward of -1, and I'm going to get a 6. So that's 5. Well, do I have to average 5 and 6? No, because I can always choose what I want to do. I want to do the best thing. So you choose study, and that gives you 6. And you don't care about this 5. The suboptimal action doesn't even enter your calculation. So this is the bad news. So unlike the expectation equation, the Bellman optimality equation does not have a closed form solution. So you can't plug it into MATLAB and get a solution out. Okay? Even if you know everything about the problem, in which case, you know, we have an MDP, we know all the states, we know all the transition probabilities. There is no closed form solution in general, but there's, again, iterative solutions that exist that form the basis of a lot of reinforcement learning algorithms. So these iterative solutions we'll see in the next lecture in more detail. Value iteration, policy iteration, Q-learning, SARSA, etc., which all share roughly the same idea of, oh, you know, let me just guesstimate some values and fill this thing randomly with zeros in the beginning. And then let me look at the Bellman equations and see which ones aren't satisfied and update these numbers to satisfy them better. And then, but then you change some of the numbers and then some other numbers are broken. And now you have to change those and you keep doing that until everybody's happy with each other and all the Bellmans are satisfied. So, so all of these 4 things are different variations of doing that. Okay, so we don't need this. And I can't cover this in the next 5 minutes, so I think for now we're good. All right, so any questions?
Is the optimal policy not probabilistic in the end?
Very good. So, as I mentioned before, there can be more than one optimal policy, even though all optimal policies give you the same value function. There is always one deterministic optimal policy, which basically chooses the maximum Q. However, there might be situations where multiple Qs are equal to each other, and there might be optimal policies that choose one or the other, or choose randomly between them. But there's always a deterministic optimal policy in MDPs. So for example, this is not true in game theory, right? So when you're solving games like poker or rock, paper, scissors, you don't always have an optimal deterministic policy. If you play deterministically, everybody knows what you're doing, they can take advantage. But with MDPs, the environment is kind of a dumb opponent. They don't, it doesn't take advantage of your deterministicness, and the probabilities that it provides you are always the same. So therefore, you can get away with deterministic policies.
So when the environment is observable, the policy is the optimal policy. There exists an optimal policy that is deterministic.
There always exists an optimal policy if you have an MDP, and it is deterministic. Yes. If the environment is partially observable, then things get more complicated, but there still exists a deterministic optimal policy. But we're not going to look into that.
So this is like a theorem, right?
Yeah.
So it's
Yes.
proven and
Yes.
like not intuitive, like not only intuitive, but
Well, I can give you the intuition. As I said, if somebody gives you a Q, so if you accept that there is a unique optimal Q, then it's trivial, right? So the policy that basically picks the maximum Q action at every state is the optimal policy, and it's deterministic. So that's the proof. Okay. All right. See you next week.